Alright, what's up guys? In this video we're going to pick up with some differential equations. We're going to be talking about exact ordinary differential equations. To ask to solve the given exact ODE, so we're given this differential equation here, 3x squared y plus y squared dx plus x cubed plus 2xy plus 3 dy is equal to 0. So let me just quickly remind you of the form for an exact differential equation. So the form that this type of equation will take is m of x comma y dx plus n of x comma y dy is equal to 0. That's our form. The first thing that you want to do is identify what m of x comma y is. So let's do that first. So m of x comma y, that's just going to be 3x squared y plus y squared. Similarly, n of x comma y, well, that's just going to be x cubed plus 2xy plus 3. Okay? Now, the first thing that you want to do is you want to run through what's known as the test for exactness. And to put it very simple, we need to take some first order partial derivatives, and if the partial of m with respect to y is equal to the partial of n with respect to x, then we can say that the equation is in fact exact and we can go about solving it. So run through the test for exactness at least once prior to starting these problems. As long as you're good with taking partial derivatives, it shouldn't be anything that takes a significant amount of time. So let's go ahead and take the partial of m with respect to y. So I'm going to go up here. We need to take the partial of 3x squared y plus y squared with respect to y. And so if we do that, we'll just end up with 3x squared plus 2y. Now we need to go over here and take the partial of n with respect to x. So let's do that, and we get the same thing. We get 3x squared plus 2y. So what we did was we ran through the test for exactness, and we can clearly see here that the partial of m with respect to y does in fact equal the partial of n with respect to x, which means that this ODE is exact. Okay. All right, so now that we've validated that this equation is exact, we need to solve it. Okay, so the first thing that I want to introduce you to is that the solution for an exact differential equation has a particular form, and that form is the following. It's going to be f of x comma y is equal to c, where c is an arbitrary constant. Okay, there's two ways you can do it. First of all, you need to find f of x comma y, and there's two ways you can do that. The first way you can do it is you can integrate m of x comma y with respect to x, or you could integrate n of x comma y with respect to y. It doesn't matter which one you choose to do, although in some cases, depending on the problem, one may be easier than the other. So in my case, I'm just going to integrate m of x comma y with respect to x. So let's do that first. You could have chosen the other one if you wanted to, but I'm going to choose m of x comma y. So in this case, we'll just have the integral of our m of x comma y, which you go up there and we see what we get. And I'll put parentheses and I'll have 3x squared y plus y squared. And we're integrating this with respect to x. Okay, so when we integrate this respect to x, it looks like we'll end up getting y times x cubed plus y squared times x, and then remember it's going to be plus h of y because we're going to have to find h of y in a little bit. So that's the first thing that you do right after you run through that test. Now what we need to do is we need to set the partial of f with respect to y equal to n of x comma y. Now here you notice that I integrated m of x comma y with respect to x, which means that when I take my partial derivatives of f of x comma y, I'm going to be taking it with respect to y. So for example, if I chose to integrate n of x comma y with respect to y, well then that will give me my f of x comma y, what I would have to partial differentiate with respect to the other variable then. So in that case it would be x if we had integrated n of x comma y first. Okay, so that's the first thing we need to do. So let's go ahead and do that. So we need the partial of f with respect to y, which is again going to be the partial with respect to y of y times x cubed plus y squared times x plus h of y. So let's go ahead and do that and see what we get. So when we take the partial derivatives here, it looks like we're going to get x cubed plus 2xy. And then remember, this is going to be h or plus h prime of y, because when we take the partial with respect to y for h of y, we get h prime of y. And now what we do, as I mentioned a second ago, is we set the partial with respect to y equal to n of x comma y, because what we're going to have to do is we're going to have to solve for h prime of y, integrate both sides to get h of y. So let's go ahead and do that. So the partial of f with respect to y, that's just going to be x cubed plus 2xy plus h prime of y. And we're going to set that equal to our n of x comma y. And remember, your n of x comma y was x cubed plus 2xy and then plus 3. And what we need to do now is we need to solve for h prime of y. What I can do is subtract x cubed minus 2xy from both sides. And if I do that, that'll isolate h prime of y over on this side. And then essentially the x cubes would subtract away, and so would the 2xy's, just leaving the 3. Now I need h of y, as I told you. So what we're going to have to do is we're going to have to integrate both sides with respect to y. So we'll integrate this side with respect to y, and then we'll integrate this side as well. And again, this is being done with respect to y. So what we're going to end up getting is just h of y, and that's going to be equal to 3y plus c. Okay, so we can go ahead and write our final answer, and we can write it in the correct form. So our final answer here, remember, your solution will take this form. So the final answer here is just going to be y times x cubed plus y squared x plus 3y. That's going to be equal to c. And that's your answer. So let me circle that for you. And that's how you solve it. All right. So that's going to be it. Let me know if you have any questions. I'll be more than happy to talk about it. So I'll see you next time.